In this video, we're going to take a look at conic sections. Now, this is going to be a pretty quick overview and look at conic sections. Obviously, you can get really deep into conic sections and yeah, do some really high level stuff with them. So let's take a look. A conic section is the type of curve you get when a cone and plane intersect in three-dimensional space. And the intersection of the cone and the plane, that object in the plane is going to be called a conic section. Now, shapes are going to be different based on how the plane cuts that cone. So when I say cone, I'm talking about the three-dimensional cone, like the one you see in this picture. It's going to go in both directions, again in three-dimensional space. Let's take a look at cutting a cone like this with a plane. So here's the cone in three-dimensional space. Obviously, this is a conical shape. There's nothing inside. And let's cut that with a line, or excuse me, not with a line, with a plane. Okay. If we cut that with a plane, then where the plane and the cone intersect are going to be this object here. In this case, since the plane slices this way, the object looks like this. In fact, we can take a look at it right here. So the object looks like this. Now, obviously, as the plane slices at different angles, we're going to create different objects. So when the plane is flat, the object here looks like a circle. As the plane gets a little bit of slope, then the object starts looking like an ellipse. Now this, I say get a little bit of slope, when the slope is less than the slope of this boundary of the cone, then we have an ellipse. When the slope is equal to the slope of the cone, that's 1 in this case, then we get our parabola. And if that slope exceeds the slope of the boundary of the curve, then we get this object, which is a hyperbola. So we go from hyperbola, parabola, ellipse, circle, and those are the types of non-trivial conic sections. Okay. Now I do want to state this. There are trivial conic sections. The trivial conic sections are when the plane passes through that singular point. So if the plane passes through that singular point, then the intersection of the cone and the plane is just that singular point. And if the slope is the same, then you can see that depending on how you draw this, either we're getting a single line, which is just the edge of the cone there, or we're getting essentially two straight lines that intersect at that point. So depending on how you draw it, two straight lines or excuse me, two straight lines or like that, or a single line if we are exactly equal at the edge. So we get a point, a line, two straight lines. But those are the trivial cases. The non-trivial cases are the ones where we don't go through that point. And those are going to be the ones that we're going to focus on. So we're going to focus on circles, ellipses, parabolas, and hyperbolas. Those four, and we're going to skip the point and the line and the intersecting lines, at least in this video. Now, that's what conic sections are in terms of how the plane and the cone intersect. When we look at conic sections and we use the plane of the XY axis, then algebraically, all conic sections can be written like this. So they are degree 2 polynomials set equal to 0 in two variables. Ax squared plus b times xy plus c times y squared plus dx plus ey plus f equals 0, where a, b, c, d, e, and f are just numbers. So algebraically, they're degree 2 polynomials in two variables set equal to 0. Again, degree 2, x squared, xy is also degree 2, y squared is degree 2. And these are non-trivial when A, B, or C is, at least one of those is non-zero. So we can get circles, ellipses, parabolas, and hyperbolas when one of the degree 2 terms is not equal to 0. If A, B, and C are all 0, then we get the trivial case where we just have a linear polynomial in two variables. The types of questions we're going to ask in this section are to identify some key components of conic sections, create standard equations for conic sections, and then identify types of conic sections from those equations. So identifying key components and creating equations means that in each conic section case, I need to know what the standard equation is. And then in the last one, we'll see how to identify conic sections from maybe non-standard equations. So let's talk about the first conic section, and that is the conic section of a circle. So if we're drawing a conic section in the standard XY plane in 2 dimensions, a circle can always be written having equation x minus h squared plus y minus k squared is equal to r squared. HK as a point is going to be the center of our circle. R is going to be the radius of the circle. And obviously the other key part about a circle is that the diameter is twice the radius. So it's the set of all points that satisfy this equation. Now, just to be clear, the center is not a point that satisfies this equation in general. If we plug in the center, we get 0 on the left-hand side equals r squared. And unless our radius is 0, then that's not a point on the circle. So this is the standard equation for a circle. Now, what does the circle mean geometrically? Well, it's the set of, geometrically, it's the set of all points which are a distance r units from the center. I've drawn a circle centered at the origin with radius 5 here. And you can see the drawing here is the radius goes out. So every single point on the circle is 5 units away from the center. And then we can move that around. We can move around HK and make it not just centered at the origin, but centered at some other point. So here's the kind of questions we would ask about finding important aspects of the circle. Let's find the center and the radius of this circle. So this is pretty easy because the equation already is in the really nice form. And so the center of this circle is going to be, one thing to be careful on is the center is actually at -9, +4. It's always x minus h. So if you get an x plus a 9, that's an h value of -9. And we have y minus 4. So my y value is a +4. So the center is at -9, comma, +4. The radius, we always say that the radius is positive. So we use the positive value of 11 here because 11 squared is 121. By the way, that means the diameter of the circle, often written as d, would be 22, twice the radius. So center, radius, diameter, that goes pretty quickly for a circle when I already have this really nice standard form. Now that's the identify key components type of question. Key components to a circle are the center, the radius, the diameter, maybe some points on the circle, but in this question it didn't ask for points on the circle. But that's identify key components of conic sections. That's the type of questions we're talking about. I can also create equations. That's the second type of question that we'll do. That's in example 2. It says, find the equation of a circle with the following properties. Endpoints of a diameter are 8, 3, and 8, 9. Let's go through that. What I generally do in cases like this is I think back to the standard equation of the circle. That is x minus h quantity squared plus y minus k quantity squared equals radius squared. So if I just know the center and the radius, then I can plug those into this equation and figure out the equation of my circle. Now the center is going to be halfway between 8, 3, and 8, 9 because those are the endpoints of a diameter. And remember, a diameter is something that goes from point to point across the circle, but through the center. So a diameter goes from point to point across the circle through the center. It is twice the radius. So the center is the midpoint of these two points. And if we calculate a midpoint, remember to do a midpoint, you actually just do the average of the x values. That's really easy in this case. 8 plus 8 over 2 gives you 8. So you knew the midpoint was going to have x value of 8. And then halfway between the y value of 3 and the y value of 9, you just do 3 plus 9 divided by 2. So you get a 6. So 8, 6 is the midpoint of the diameter. This one was really easy because all we had to do is basically find halfway between the y values. The x values were going to obviously be 8. Now, the radius is the distance from the center to a point on a circle. Well, endpoints of a diameter are points on a circle. So from the center to point on the circle, you can use the distance formula if you like. The distance formula is equal to the square root of, x2 minus x1 quantity squared plus y2 minus y1 quantity squared. That's basically the Pythagorean identity. C equals the square root of a squared plus b squared. Pythagorean theorem. So if you want to use that distance formula, that's perfectly fine. But in this case, it's a little easier. Going from 8.6 to 8.3, that's obviously a distance of 3 because the x values are the same. Going from 8.6 to 8.9, again, that's obviously a distance of 3 because the x values are the same. We just need to measure the distance from 6 to 9 or the distance from 6 to 3. Since I always use a positive value for my radius is 3. So now I know the center. Now I know the radius. I didn't really need this distance formula, but it is there if we need it. And now we say, I know what the equation of a circle is. It's going to be x minus 8 quantity squared plus y minus 6 quantity squared is equal to 3 squared, which I'm just going to write as 9. So if I know the center and the radius, then I know the equation of the circle. Center is midpoint of the diameter, radius is distance from the center to some point on the circle. Here we have 2, and you can measure both distances. So that is the second type of problem, finding an equation for a conic section. Now, like I said, circles are fairly interesting geometrically. Oops, that's pretty fast. As we go around the circle, as we take our points around the circle, all that we're looking at there is essentially every point is going to have distance from the center that is our radius. In this case, that's 5, but in general, that's what it's going to be. So you can change the radius to anything you want. So geometrically, that's what's happening with our circle, and our equation is pretty straightforward. Our equation is just this, and the information is that the center is HK, radius is R, diameter is the line that goes from point on our circle through the radius, hits another point on our circle, line segment that does that. So it's twice the radius. So circles are fairly nice conic sections to deal with. Now, another type of conic section that we're going to look at is the parabola. There are going to be two versions of parabolas that I can draw in the XY plane. One of the versions is going to be parabolas which point up and down. The other version is going to be a parabola that points left and right. Now, the information that we're going to be using, so we're going to have two different types of equations. This first one is the one that's going to point up and down. And the second equation is going to be the one that points left and right. Notice that on one of these, the part with the x is being squared, and the part with the x is the x minus h, I'm saying. And the other part, the part with the y, which is y minus k, is not being squared. So the x part is being squared in one. In the other, the y part is being squared. In the first one, the y part is not being squared, but the x part is. And the part that's not being squared is being multiplied by something, by some number, which we denote as 4 times p. Now, the reason we don't denote this as something else is because this value of p is actually giving me how far a focus is from my vertex and how far a directrix is from my vertex. Those words might not make sense, so let me talk about what they are geometrically. Okay, so here we have a picture of a parabola in red that's pointing to the left. This is what I would say parabola pointing left. The vertex is going to be, in this case, at the point 0, 0. The vertex is the bottommost, topmost, leftmost, or rightmost point of the parabola, depending on how the parabola points, if it's up, down, right, or left. Now, the two key features of a parabola are this vertex, which is a point that's sort of in the interior of the parabola, and this directrix, which is a line outside. Now, if the line points left, then the directrix is going to be on the right-hand side. So if the parabola points left, then the directrix is going to be on the right-hand side of the parabola. And it turns out, if you take any point on the parabola and you measure the distance to the focus, and then take that point and measure the distance to the directrix, these two values will be the same. So a parabola geometrically can be defined as the set of all points where the distance from the point on the parabola to the focus is equal to that same point distance to the directrix. The same point's distance to the directrix. So here's what we have. Again, the vertex in this case is the rightmost point. It, in this case, is the origin. I try to make things simple. It turns out if you do the calculations, and we will do the calculations here, the focus is 3 units from the origin. And because it's in the interior, we have to move 3 units to the left. And therefore, the directrix is also 3 units from the vertex, or 3 units from, in this case, the origin. We have to move in the opposite direction. So the directrix is this vertical line, x equals 3. The focus is the point -3, 0. And I've done the calculations here. But as you move your point on this parabola, if you calculate this distance here and this distance here, they will always be the same. So geometrically, the set of all points whose distance to the directrix is the same as the distance to the focus is going to form my parabola. It's going to be my parabola. So that's the idea. Okay, always this distance is equal to this distance. And because of the way the parabola is shaped, it has a lot of nice other properties too that work in physics. Like if you shoot a line into the parabola, when it bounces, it'll bounce and hit the focus. This is why a lot of signaling devices have parabolic shapes, like a satellite dish has the parabolic shape so that when it's pointed in the right direction, a signal will hit there and then bounce to the focus, and they put the receiver at the focus. Also, it works in reverse as well. So with some lighting, a lot of those are parabolic shapes. So as the light emits away from this point, which is the focus, it'll bounce off and then shoot straight. So if you want a nice spotlight, what you do is you make a parabolic reflector. You put the light source at the focus, and then you turn it on and you get a nice spotlight. And there's a lot of other like lenses or sometimes parabolic shaped things like that. Now we could do a really deep dive into applications of parabola, but that's not the point of this class. In this class, we're just going to focus on the equation, the vertex, the focus, and the directrix. Remember, I said this equation is going to be the one where the parabola is pointed up or down. Oof, I didn't do that very well. This equation is going to be the one where the parabola is pointed right or left. The one where we square the y versus the one where we square the x. When you square the x, we're pointed up or down. When you square the y, we're pointed right or left. Okay, and by the way, whether it's up or down depends on whether p is positive or negative. Whether it's right or left depends on whether P is positive or negative. So let's take a parabola and let's find the focus, the vertex, and the directrix of this particular parabola. Now, notice that this one, unlike the circle example, is not in the really nice form that we like it to be in. We'd like it to be into one of these two forms, where we have a perfect square equaling 4p times the linear piece. This does not have that form yet, but I can force it to have that form. I'll show you how we can force it to have that form in just a moment. But once we force it to have that form, then we'll look at the vertex, focus, and directrix of the parabola. Now, like I said, we want a perfect square, and the only component that's being squared here is the y. So I know that what I'd really like to have is an equation of this parabola. I know it's a parabola because I was told it was a parabola. That looks like this. So I want an equation that looks like this. That means I need to get a perfect square with variable y on the left-hand side. So I do my standard thing. When I want a perfect square, I subtract x from both sides. And on the left-hand side, I create just y squared plus y. And then I'm going to add some unknown value in here to create a perfect square. Now, the question is, what unknown value am I going to have to add to that left-hand side? So what's the value that I need to add or subtract? When I do that, I'll have to do the exact same thing. On the left, excuse me, on the right-hand side. I see what's going on. So that value we'll just leave blank for right now. I know I want this y minus k squared on the left-hand side. Now, the minus is not the key component. You can do a y plus something squared, and then we know that something is negative. But what I'm going to do is I'm going to do a completing the square process. When I do a completing the square process, remember we take the coefficient of my y term, as long as again, we start with coefficient of y squared being 1, then I look at the coefficient of my y term. Since that's a 1, I cut that in half. And then I say, well, y plus 1/2 quantity squared would give me y squared plus 1y plus a fourth. So we add a fourth to both sides. The way I'm getting a fourth is I'm just squaring that 1/2. So I take this coefficient, divide by 2, put it here, square that number, and then put it there. If I added 1/4 to the left-hand side, I also need to add 1/4 to the right-hand side. Now I have the square term where I wanted. I wanted to have y minus k squared on the left-hand side. I now have that through a process of completing the square. So I'm ready to go. But on the right-hand side, I don't quite have what I want. I want to have an x minus h inside of the parentheses. So what I'm going to do is I'm going to factor out any coefficient of x. In this case, if I factor out a -1, I get x minus 1/4 on the right-hand side. So negative quantity x minus 1/4. And then usually I just leave the equation like that. Once I see the equation like that, then we can say our vertex of this parabola is 1/4 comma -1/2. That's just h comma k in this equation. Now, I have a negative out here. So it turns out that knowing that I have a negative and knowing that my equation looks like this, I know that a negative p is going to cause my parabola to point left. You can see why that would be. Because essentially this negative, if I pretended this was at the origin, then I would have all negative x values. If I move it down to wherever my vertex is, this negative forces negative side of my vertex, the left-hand side of my vertex. So the focus is going to be somewhere in here. So I simply need to take the vertex and move it p units to the left. The directrix is going to be a vertical line over here. So I take my vertex, which I already know, and I move that to a vertical line p units to the right. So the focus moving to the left, that means in the x direction. Here, -1 is equal to 4p. So I should have said this, but p is equal to -1/4. Let me write that down over here. P equals -1/4. So P is -1/4 because 4P is -1. So I'm going to move from the vertex left, or I'm going to take the vertex and subtract 1/4 in the x direction. If I subtract 1/4, I'll get a 0, comma, -1/2. So that's where my focus is. My focus is at 0, comma, -1/2. And then my directrix, since it's a vertical line, it's going to be x equals. And I'm going to add 1/4 to the x value of my vertex. 1/4 plus 1/4 becomes 1/2. Again, I got that by adding 1/4 plus 1/4. And again, the 0 I got by taking 1/4 minus 1/4. That's how I got the 0. So my directrix is the vertical line, x equals positive 1/2. My focus is 0, negative 1/2. And that all came from P being negative 1/4 and knowing that I need to move in the x direction back and forth. You can graph this if you'd like to just confirm that we got what we want. You can graph it on Desmos to confirm. You can also graph it on your calculator, although you'd have to graph just one side of it in this case, because this is not a function. So here it is graphed out on in Desmos, although again, you don't have to do this by any means. Just so that we're all on the same page, like we said, the focus is 0, negative 1/2. So it's that point in here. And then the directrix is the line x equals positive 1/2. That's this line here. And every point on this parabola is equidistant to the focus and the directrix. So this is the idea. It's always nice to kind of sketch it. I know it's tough for uh, me on this video to sketch graph by hand, but we try to. So that's how we can find the vertex, the focus, and the directrix of this parabola. Again, this did not have the nice standard form, so we just used completing the square to make it have this nice standard form. In particular, this was the standard form, the second one. Obviously, if the x squared term was present, we'd try to use the first standard form, which happens to be our next example. So let's use the ideas in example 3 to find the vertex, focus, and directrix of this parabola that we have in example 4. Pause this if you want and do it on your own if you'd like. Now I can clearly see that in this case, the x squared term is the one that's being squared. So the x term is going to be the one that's being squared. Therefore, I know that I'm going to be utilizing the equation of this form. X minus h squared equals 4p times y minus k. That's the one that's going to force the parabola to be pointing up and down. Up when p is positive, down when p is negative. So I need to transform my equation into something that looks like this. Once again, completing the square is going to be the way to go. So we're going to get x squared minus 2x on the left. And on the right, I'm going to subtract 8y from both sides. So on the right, I'll get minus 8y. I'll subtract 9 from both sides. So on the right, I'll get minus 9. In this case, if I want a perfect square, I got to figure out what to add or subtract. Well, it'll always be add on the left. When I do that, I'll have to also add or subtract, which will always be add, something on the right as well. Now, I know I want my perfect square to be x minus h squared. At this point, I can say since the coefficient of x squared is 1, this -2 will have that, and that'll become my h. I shouldn't say the -2 will become my h. So when I do a -2, I half that, and I get x minus 1 quantity squared inside there. Then I square -1. -1 times -1 is a +1. So that tells me I need to add 1 to both sides. Combining like terms on the right-hand side gives me -8y minus 8. And then I usually factor out the coefficient of y so that it looks perfectly in line with my equation. When I do that, I end up with the equation of the parabola being x minus 1 quantity squared is equal to -8 times y plus 1. And it's pretty obvious that p here is a -2. So -8 is equal to 4p, so therefore p is -2. Since p is -2, I know that this parabola, so this is the equation of the parabola rewritten. I know that that thing is actually going to be a parabola pointed down. I knew it was going to be pointed up or down. Now that I know p is negative, it's going to be pointed down. And that means that whenever I find my vertex, to get to the focus, I'm going to go down p units. To get to my directrix, well, my directrix is going to be a horizontal line, and I'm going to go up p units to get to that. So, in other words, I can clearly see that the vertex is h of 1, k of -1. So the vertex is 1, comma, -1. The focus is going to be what I get when I start at the vertex. So I'm going to start at 1, -1. And then because I have to move down p units, or down, I'm going to subtract 2 from the y value in this case. So the vertex is 1, -1, and the focus is 1, -3. Notice in the last example, I changed the x value because my focus from vertex was a movement left and right. Here, I changed the y value because movement from the vertex to the focus is up and down. Directrix, it's a horizontal line, so it's going to be y equals. I take the y value of the vertex, and then in this case, I add 2. So the directrix is going to be the line y equals +1. Focus is at 1, -3. Directrix is y equals 1. Vertex is at 1, -1. And there we go. That's the entire thing. That's what I was trying to find. Obviously, if you want to confirm that, you can graph on your calculator. This one is an easy problem to solve for y, so you can solve that for y if you'd like, and then graph it on your calculator. You can also graph it on Desmos, which is what I'll show you right here. Here is that parabola. I've graphed it in red. The vertex obviously is at 1, -1. Y equals 1 is the directrix. The focus is at 1, -3. Again, that focus is a very important part. It's not a point on the parabola, but it's definitely related to that parabola. And geometrically, it's how we generate the parabola. Physically, it's the really nice point that when you bounce off, you go different places. So that's the idea here. And this is the graph of that. In examples 3 and 4, we had to do a completing of the square to get my parabola into one of these two forms. Obviously, if my parabola was already in one of those two forms, the problem would take a lot less work. And that's the same thing as before. We saw that with the circle was already in this form. If the circle's not in this form, then we could complete the square with the x, complete the square with the y, and then force it into that form. Obviously, we didn't do an example like that, but whenever you want, you can do that. Most of the equations I give tend to be of the standard form, but I did want you to at least a couple of times remember how to complete the square and get perfect squares when we need them. So now let's take a look at the other side. Let's find the equation of the parabola whose vertex is at 5, 4 and whose focus is at 3, 4. I'm going to do this algebraically, but I'm going to think graphically. So when I go ahead and do this, I am going to think on the graph what's happening. We have 5, 4, and 3, 4. Now, the first thing I do is I look at these 2 points, 5, 4, and 3, 4. 5, 4 is the vertex, and 3, 4 is the focus. In this case, that means my parabola is going to go through 5, 4. And since the focus is to the left, I know that roughly speaking, my parabola is going to point to the left. So it's going to point to the left. It's going to go through vertex 5, 4. And I'm saying it's pointing to the left because it has to, because the focus is to the left of the vertex. Notice, by the way, that the distance from the vertex to the focus is a 2 or a -2 as your p-value. So we're going to get a p-value of -2 there when we get that. So that's kind of all we need. We see here that we point to the left and that the p-value is -2. Now, The other thing I wanted to mention is that you don't have to always graph this on a nice grid paper. Most of the times when I'm doing this by myself, I just take some scratch paper and I graph it. And I say, oh, 5, 4 is roughly this spot. I know 3, 4 is to the left, and therefore I know parabola is pointing left. So just by a quick understanding, parabola points left, and we just saw that the p-value is going to be a -2. Okay, because that's the distance from the vertex to the focus. If the parabola points left, then that's where we're squaring the y part. We're getting y minus k quantity squared is equal to 4p times x minus h. Now that I know my vertex is 5, -4, I can plug in the h and the k. I'm sorry, not 5, -4, 5, 4. I can plug in the hk. So I'm going to get y minus 4 quantity squared equals 4p times x minus 5. That's coming from the vertex. The vertex is 5, 4. Now that I know p is -2, I can replace the p with a -2, and then -2 times 4 is a -8. So in this case, parabola points left with p of -2. I know it's going to look like that form. I just plug in the vertex as hk and plug in the p of -2, and we're done. That's the equation that we're asked to find, the equation of the parabola with these two properties. Obviously, we don't always have to be given just the vertex and the focus. We can be given other information for our parabola, and that's what example 6 does. Find the equation of the parabola with the following properties. The parabola has directrix, which is x equals -2, and focus of the point 3, 4. Once again, I'd probably sketch this. In fact, I don't need to use a nice grid paper or anything. I can just say, let's pretend 3, 4 is some point right here. X equals -2. Well, x equals -2 is going to be to the left of the point 3, 4 because the point 3, 4 has x value of 3. So my focus is going to be here. My directrix is going to be a vertical line, x equals -2 over here. That means my parabola is going to be pointing to the right. Since my parabola points to the right, I know what kind of form we're going to have. We're going to have the y minus k squared form. And also, since the directrix is p units away from the vertex, and the focus is p units away from the vertex, I can see that the vertex is going to have the same y value as the focus, but the X value is going to be halfway between the directrix and the focus. So the vertex is going to be halfway between the directrix and the focus. So I'll be able to find the vertex that way. But this all starts from knowing how we're pointing. And again, all I have to do is sketch it. It can be as simple as a sketch of what as the thing I'm drawing here. We are ready to do the problem. The parabola points right. So I know it's going to have the form where we do the y minus k squared. That's what I just said. The vertex is, I'm going to just say roughly, not roughly, is halfway between the directrix and the focus. It's equidistant from the directrix and the focus. That's going to force it to have y value of 4 and the x value is going to be halfway between x of -2 and an x of 3. Halfway between can always be found by adding up and dividing by 2. So my vertex is at 0.5, comma 4. The distance from the focus to the vertex is the p. So distance from focus to vertex is p. And that's obviously a 2.5. So if I start at the vertex of 0.5 and go to the focus of 3, I get 2.5. It's going to be a positive 2.5 as well because I know my parabola points right. Now I am ready to plug in these two pieces and find the equation I was looking for. So my equation is y minus 4 quantity squared equals 4p times x minus 0.5 or 0.5. Since p is 2.5, we take 4 times 2.5. That would give me a positive 10. And again, you can double check this if you want by graphing it. I am not going to do that in this problem. But there we go. So that's the basics. We say distance from focus to the vertex, or from the vertex to the directrix. You could have also used vertex to the directrix. We see is 2.5. It's a positive 2.5 because we're pointing to the right. We knew that from where the focus was in relation to the directrix. And then we can just fill in our equation. And that's what we're looking for. This is what we're asked to find. The equation of that parabola is, in fact, this one. The next type of conic section that we're going to look at is the conic section of an ellipse. Now, ellipses are going to have two types of equations. One, which is x minus h quantity squared divided by a squared plus y minus k quantity squared over b squared is set equal to 1. And the other where we exchange the a squared and the b squared. So the b squared is under x minus h quantity squared, and a squared is under y minus k quantity squared. Now, the difference between these two equations has to do with this assumption that we're going to make that a is the bigger number. If a is the bigger number, then what's going to happen in this first type of equation is that the ellipse is going to be stretched out more in the x direction than in the y direction. If the a squared is underneath the y minus k part, then it's going to be stretched out more in the y direction than in the x direction. Now, h, k, those are going to be where the center of the ellipse is. But again, the important difference between these two equations is that stretched out in the x direction more, I didn't draw this very well, or stretched out in the y direction more. Whatever bigger number is underneath, if the bigger number is underneath the x part, then we're stretched out in the x direction more. If the bigger number is underneath the y part, then we're stretched out in the y direction more. That's going to be important because when I create my center, an ellipse is going to have two foci. If it's stretched out in the x direction, the two foci are going to be moved right and left from the center. And if we're stretched out more in the y direction, the two foci are going to be moved up and down from the center. I know that's pretty poor drawings, but that's what's happening. So here is the information for an ellipse. Like I said, the center is at the point h, comma, k. The major axis, which is the longer one, is going to be of length 2a. And we say that there are vertices on the end of the major axis. So the points on the ellipse at the end of the major axis are what we call the vertices. The minor axis has length 2b. That's obviously the shorter axis. And we say that the points on the ellipse at the ends of the minor axis are called covertices. Some books will use vertices as well. Some books use covertices. Some say we have 4 vertices. Others say vertices and covertices. I think vertices and covertices are a little bit easier to understand. Major axis, the longer one, vertices. Minor axis, the ends are covertices. Now, like I said, with the ellipse, we're going to have 2 foci. Foci is a plural of focus. And they're going to be located along the major axis, c units from the center. Now, for an ellipse, the way we find c is that c squared is equal to a squared minus b squared. So c squared is equal to a squared minus b squared for the ellipse. And then there's this thing called eccentricity. That eccentricity is a rough value of how much your ellipse is stretched out. The closer it is to 1, the more stretched out it is. The closer it is to 0, the more circular it looks. So the eccentricity is just the ratio of c to a. So it's c divided by a as a number. Now, geometrically, why these foci are important is because they serve a specific role. Let me actually show you this before I read off what it's doing. So here I've graphed an ellipse centered at the origin. So the ellipse is actually this one, x squared over 16 plus y squared over 25 is equal to 1. And when you do the calculations for C, C is equal to 3. So the two foci are located 3 units away from the center on the major axis. It's pretty easy to see that this ellipse is stretched out more in the y direction than it is in the x direction. It's stretched out 5 units in the y direction. By the way, we would then therefore say the vertices of the ellipse are 0, 5, and 0, negative 5. So 0, 5, 0, negative 5 are the vertices for this ellipse. The co-vertices for this ellipse are 4, 0, and negative 4, 0. So vertices 0, 5, 0, negative 5, co-vertices 4, 0, negative 4, 0. Now here's the interesting thing about the two foci in relation to points on the ellipse. If you look at the distance from the first focus to a point on the ellipse, and then take a look at the second focus and calculate the distance from the second focus to the point on the ellipse. When the point on the ellipse changes, these two distances are going to change. However, a really interesting thing happens to the sum of the two distances. When I add these two distances, I end up getting a sum which is 10. So for this particular point, it looks like the distance from the first focus to that point is about 3.72. And the distance from the second focus to the point is about 6.28. If I add those two up, I get a 10. If I change to any other point, the distances individually will change, but the sum of the two distances always adds to 10. Now it's 10 for this ellipse. Obviously, for other ellipses, it would be a different number. But no matter what point you're at, the two numbers are going to change. Here we have essentially 8 and 2 adds up to 10. So the two numbers are going to change, but they're always going to add up to 10. For this ellipse. Again, if it's a different ellipse, then it'll be a different number. But that's one reason that ellipses are nice geometrically. There is also some physics applications of this. If you put yourself at this point in a room that's elliptical shaped, it turns out the audio here at the focus, at one of the foci, or at a single focus, is also good from sound bouncing on and off the walls. But so there's some other interesting things as well. But geometrically, we see that an ellipse can be formed by just taking the two foci and saying that if I look at all points where the sum of the distance from focus 1 to that point and plus the distance from focus 2 to that point is a constant, then that'll form the ellipse. So that's what I had on this slide. An ellipse is a set of all points where the distance from point to first focus added to distance from point to second focus is some constant number. Again, in our example, it was 10, but in other examples, it would be other numbers, some other constant. Now, that's really nice geometrically. For this class, we're going to be focused not on the geometrics of the conic sections, but I do always want to mention those. What we're going to be focused on in this class is the idea of what are the properties of the conic sections? Can I derive those? Can I figure those out? And then can I come up with the equations for conic sections? So let's do an example. This one says find the center foci, vertices, and eccentricity of the ellipse given here. This ellipse is really nice because it's in standard form. So to find the center, foci, vertices, co-vertices, and eccentricity of the ellipse, we can use all of the properties we saw before, specifically this information. Okay, so the first thing I want to do is make sure I'm aware that this ellipse is stretched out more in the y direction because we have the bigger number in our denominator underneath the y squared part, in particular y minus 1. So that means the major axis is going to be the one in the y direction. Now, it's not going to be the y-axis because we need to be the vertical axis, but it needs to go through the center. So that's what's going to happen. All right. So the center is going to be at HK. In this case, that's 3, 1. Again, H is X minus H. K comes from Y minus K. So the center is at 3, 1. Let's do the vertices. So the vertices, since we are stretched out more in the y direction, the vertices are going to be move up and down from the center. So we're going to have a center. To get to the vertices, we're going to move up and down. And what do we move up and down? Well, we're going to move up and down the square root of 25. So what I'm going to do is I'm going to start at the center. For one vertex, I'm going to move up 5 units. So I'm going to take 1 plus 5. That's going to be a 6. For my other vertex, I'm going to move down 5 units. So I do 3 comma 1 minus 5. And so my other vertex is 3, negative 4. That's the one on the bottom. 3, 6 is the one on top. Related to this is that the length of the major axis is 10, right? We went 5 units down and 5 units up, so the total length of that major axis is 10. Now, some people call the minor axis endpoints vertices as well. I tend to call these co-vertices. I think that's a little bit easier to deal with, a little bit easier to, it's not that it's hard to understand, but it's nice having that distinction anyways. It's easier to have the distinction. So I'm going to call them co-vertices. And to get to the co-vertices, I'm going to move 4 units, that's the square root of 16, in the x direction. So the minor axis is the axis in the x direction. So to get to my co-vertices, I'm going to start at the center, and I'm going to add 4 to the x value, and then subtract 4 from the x value. Move 4 units in either direction. When I add 4 to the x value, I get to the point 7, 1. When I subtract 4 from the x value, I get to the point -1, 1. By the way, since co-vertices are 4 units from the center, that means that the length of the minor axis is a double 4. Now, the other thing we want to do is so we've found the center, we've found the vertices. In order to find the foci and the eccentricity, I need to calculate this special C. And for ellipses, C squared is equal to A squared minus B squared. By the way, since A is bigger than B, and we have A squared minus B squared is equal to C squared, C is also going to be always less than A, just based on this formula. So C is always less than A there. So C squared, in this case, A squared is 25 and B squared is 16. So we get 25 minus 16, which is obviously 9. So C is equal to 3. By the way, this was a very similar ellipse to the one I had graphed earlier, except now we're just at a different center. So C is 3. Therefore, if I want to find the foci, I can start at the center, start at point 3, 1. And then because we're stretched out more in the y direction, I'm going to add and subtract 3 from the y value. So the two foci I'm going to get by adding and subtracting 3 to the y value of the center. That means my first focus is 3, positive 4. And my second focus is 3, negative 2. Now, the last thing that we're asked to calculate is the eccentricity. The eccentricity is just C over A. Like I said, because of the way this formula works, A is always going to be the bigger value. So this fraction is always going to be a fraction between 0 and 1. They're both positive, so always going to be a fraction between 0 and 1. And in this case, it's 3/5 or 0.6, depending on whether you want to use decimals or fractions. So those are the properties of this ellipse. If you want to graph the ellipse using your calculator, it's kind of cumbersome to solve this for y. With Desmos, it's not too bad at all. But if you want to graph and confirm that, you can. I'll do that in this case, but in general, I probably wouldn't do that. So I graphed that in Desmos, and we do see we get an ellipse stretched out more in the y direction than in the x direction. The center there is 3, 1. And obviously 3, 6, 3, -4 are my vertices. My co-vertices, oh, can't get that to click. My co-vertices are, what's going on here? Not sure what's going on there. Why that's not graphing. Well, let me just, they should be at 7, 1 and the point -1, 1. Okay, so they should be at -1, 1 and 7, 1. And then obviously my foci, since we're stretched out more in the y direction, those were at 3, 4, and also 3, -1. Or excuse me, not 3, -1, -2. So there we are, 3 units from each. So those are the two foci. This was an ellipse. It's not super circular. The more circular it looks, the closer the eccentricity will be to 0. The more stretched out it looks, the closer the eccentricity will be to 1. So this was an eccentricity of 0.6. If it were closer to 0, it looked more like a circle. If it were closer to 1, it'd be way more stretched out. Let's try another example. In example 8, it asks to find the features of this ellipse. Now you may say, which features are we talking about? Well, the features that we had listed on the information slide. So the center, the vertices, the co-vertices, the lengths of the major and minor axis, the foci, and the eccentricity. Push pause on the video if you'd like to try this on your own. Otherwise, in a couple of seconds, I will do it. All right, so the first thing I want to notice is that the bigger number is underneath the x part. So this is stretched out more in the x direction. All right. So we're stretched out more in the x direction. That means when I do all of my calculations, the foci and the vertices are going to be moved from the center in the x direction, left or right. So they're going to move some units in the x direction. And my co-vertices are going to be moved up and down. That's how I get to my co-vertices. So we start at the center. The center is going to have value negative, I mean, it's going to be the point -5, 9. That's the HK that we're given here. Since we're stretched out more in the x direction, the major axis is the axis of x direction. The vertices are going to be moved, well, 8 units left and right. So I'm going to take the -5, 9, and I'm going to add 8 to the x value. And then I'm going to take the -5, 9, and I'm going to subtract 8 from the x value. -5 plus 8 becomes a 3. -5 minus 8 becomes a -13. Since we moved 8 units in each direction, the length of the major axis is double 8, which is 16. You can always also say how far from distance from 3 to -13. You could have done that as well. Now the co-vertices are going to be found when you move up and down. And we're going to have to move up and down 6 units. Since b squared is 36, b is 6. So we start at the center, which is -5, 9. And then we add 6 units to the y value. And then subtract 6 units from the y value. 9 plus 6 gives a 15. 9 minus 6 gives a positive 3. Since we moved 6 units in each direction, length of the minor axis is 12. 6 times 2 is 12. And now the last couple of things I need to find, the foci and the eccentricity, both require me to figure out what that C value is for ellipses. Well, a squared, a is always the bigger number, so in this case that's 64, minus 36. 64 minus 36 is 28. That means C is the square root of 28. Obviously, that's an irrational number. If you wanted to simplify it, it could. You could do some factoring and simplification, but I am not going to do all that simplification. I'm just going to call it square root of 28. And I'm going to say, therefore, since I know my foci are on the major axis, and my major axis is going in the x direction, parallel to the x-axis, we can add square root of 28 and subtract square root of 28 to the x values. Therefore, my first focus is going to be -5 plus square root of 28, comma 9. And my second focus is going to be -5 minus square root of 28, comma 9. So we start at the center and we move square root of 28 units right and square root of 28 units left. If you wanted an approximate value, you can figure out the approximate value of that. The eccentricity is going to be the square root of 28 divided by 8. Again, C was square root of 28. A is 8 because A squared is 64. Therefore, square root of 28 over 8 is my eccentricity. I'm going to leave it like that, but I am going to, on this one, give a decimal version of that. Square root of 28 divided by 8 is about 0.66. Again, notice it's between 0 and 1, roughly about 0.66. If you want to confirm all of this information, you could graph it. Again, I tend not to. I tend just to leave it as is. But you could confirm all of this information by graphing my equation. This is how to find all of the features of an ellipse given the standard equation for the ellipse. Now, if we weren't given a standard equation, I'm just going to say if we weren't given a standard equation, you could use completing the squares with some clever dividing to make this all work. Which I tend not to give people, but we could do that. Now let's do the other side. Let's find equations, or an equation, I should say, for an ellipse with certain properties. So the properties that I'm given are that the vertices of the ellipse I want to find are at 3, 1 and 3, 9. I'm also told that the minor axis has length of 6. Now, this is pretty straightforward as far as creating the equation for the ellipse. The only thing I really need to do is figure out which part has the larger number and which part is divided by the smaller number. So when I take x minus h squared, am I dividing that by the a squared or am I dividing that by the b squared? And the same is true, the reverse of that will be for y minus k squared. So one of these will be a squared, one of these will be b squared. Okay. It says the vertices are at 3, 1 and 3, 9. Well, again, if I kind of just sketch this out in my head or just sketch a really easy sketch on the graph paper, 3, 1 and 3, 9 are aligned vertically. And so therefore I know that this ellipse is stretched out more in the y direction than it is in the x direction. And I'm going to overly dramatize that when I actually draw it. So that means the smaller number is underneath the x minus h squared. The bigger number is underneath the y minus k squared. Okay. Now, vertices being at 3, 1 and 3, 9 means that right in between, the midpoint of those two vertices should be the center. In this case, halfway between 1 and 9, I would take 1 plus 9 and then divide that by 2 and get a 5. So the center is at the point 3, 5. And that also means that the length from the center to one of the vertices is 4, or that the length of the major axis is 8. So that means A is 4 as well. And since the minor axis has length 6, that means the minor axis of length 6 forces B to be 3. All right. I could have said the major axis is length 8 if I wanted to. So my equation that we have can now all be filled in. I know the HK, that's my center. I know the A is 3, excuse me, the A is 4, the B is 3, excuse me. So if B is 3, then the denominator underneath the X part is going to be 9. If A is 4, the denominator underneath the Y part is going to be 16. Since the center is at 3, 5, that means H is 3 and K is 5. So I get the equation for the ellipse as x minus 3 quantity squared divided by 9 plus quantity y minus 5 squared divided by 16 is equal to 1. And that's it. That's the whole thing. Now, if you wanted to, you could also, we find the vertices here, find the co-vertices if I wanted. The vertices were given, but I could have also now found the co-vertices, and I could have used this equation to find my C, and that could have given me the foci and the eccentricity. I won't do that in this case because it only asks for the equation. So here we found the equation of the ellipse that we were looking for. Let's try example 10. Find the equation of the ellipse with the following properties. The center is at 1, 2. One focus is at 6, 2. And one vertex is at 7, 2. Push pause. Try this on your own if you'd like. In a couple of seconds, I will show you how it is done. Okay, so here we go. First thing I do is I kind of decide what the equation is going to look like. The center is going to be at point 1, 2. To get to the focus of 6, 2, I have to move to the right. And to get to the vertex of 7, 2, I also have to move to the right. Therefore, because of the way this is, because I know that the focus is going to be on the major axis, and now I know the major axis is parallel to the x-axis, I know that my ellipse is going to be stretched out more in the x direction than in the y direction. So that means the equation I'm going to get is the reverse of the equation, not the reverse, but rather I'm going to switch up from our last example, and the bigger number has to be underneath the x. The smaller number has to be underneath the y. Now the center obviously is given to me. The center is 1, 2. That gives me the h and the k. The vertex being at 7, 2, well, I know that A is the distance from the center to a vertex. Therefore, I know that A is going to be 6. The only thing that's left is to find the B. If I have the H, the K, I have the A, I only need to find the B to complete this equation. Now it doesn't give me the B, but it does give me the focus. And I know that the distance from the center to the focus, to one focus, is C, which in this case would be 5. I also know that there's this relationship that says in an ellipse, C squared is equal to A squared minus B squared. Since I have A and C, I can use those two values to find B. C squared is going to be 25. A squared is going to be 6 squared, which is 36. If I take 36 minus 25, I get 11. So what we're saying is that B squared, if I add B squared to both sides and then subtract 25 from both sides, I get B squared is equal to 11. Or some people would write B is equal to the square root of 11. Now I'm ready to write my equation. Now, conveniently for me, I'm using a B squared in the denominator. So we get x minus 1 quantity squared plus, divided by a squared. A squared, 6 squared, that's 36, plus y minus k squared. K here is 2, so y minus 2 squared. And then I divide by b squared. Now my b squared is 11. My b is square root of 11, so b squared is 11. Be careful on that, b versus b squared in this case. And that's it. That's the equation of the ellipse that I was looking for. X minus 1 squared divided by 36 plus y minus 2 squared divided by 11 is equal to 1. Obviously, there's other ways to, find your A's and B's and centers. We've, in the last couple of problems, found the center, one of them the center by finding a midpoint. Here, we were just given the center. In the first problem, we were given the A and the B. Here, we're given the A and the C, and then we have to use the equation for the ellipse of C squared equals A squared minus B squared in order to find the B. So lots of different ways we can do that. those are the types of problems we do for the ellipse. We're either going to start with one of these two equations and then find these informational pieces, these features, or we're going to start with these features and find the equations, or at least some of those features, and find the equations, or the equation, excuse me. So there and there. Notice that the equations of the ellipse, we have x minus h squared over a squared plus y minus k squared over b squared. Or we swap the a and the b. But we have a plus in here. For the next conic section, the next conic section is going to be the hyperbola. And the equations are going to look very similar, except we're going to have a minus in between those terms on the left-hand side. So one equation is going to be x minus h squared over a squared minus y minus k squared over b squared is equal to 1. And the other equation is going to be the quantity y minus k and quantity squared over a squared minus quantity x minus h and quantity over b squared over b squared equals 1. So the key thing here is not whether or not the bigger number is A or B. In fact, some of these will have bigger number as B and smaller number as A, and others will have bigger number as A, smaller number as B. The key part here is which term is being subtracted. Is the y minus k squared term being subtracted, or is the x minus h squared term being subtracted? And the reason for the important difference is the way the hyperbola is going to point. So remember when we looked at how the plane intersects the cone, we saw a hyperbola. I could have the hyperbola point up and down, or I can have the hyperbola point left and right. It turns out in this first equation, the hyperbola does this. It points left and right. So it's going to have two parts, a right-hand part that points right and a left-hand part that points left. In this second type of equation, I'm going to have a hyperbola that essentially points up and down. So it's going to have two parts. One part points up, one part points down. The way I remember how to do this is that the center of the hyperbola is going to be HK. In this one, if I start at the center, if I think about this term having value of k, so y is equal to k, imagine this term is gone. I have an opportunity to move in the x direction to make this equation true. There is some x value that can make this equation true. However, if I cancel out this term, there's no opportunity to move in the y direction to make this equation true. And that's obvious because on the left-hand side, I have a negative number. And on the right-hand side, it's equaling to positive 1. So that means moving in the y direction, I can never hit a point if I start at the center. And the reverse is true. in this case, if I think about getting rid of that term, there's no way I can start at the center and move strictly in the x direction to hit something because of this negative value there. I get negative a number is equal to 1. And because of the squareds, these will always be positive. So that's kind of how I remember which way my hyperbola is pointing. When the x values are positive, when the x component is positive, then we're pointing right and left. When the y component is positive, then I'm pointing up and down. Now, here's the information that we're going to be looking at in the case of a hyperbola. First of all, the center of the hyperbola is going to be the point HK. That is not actually on the hyperbola. We are going to have a transverse axis and a conjugate axis. The transverse axis is the one that goes from vertex to vertex. There's going to be two vertices here. The two vertices are both going to be A units from the center. You're either going to get those moving left and right or up and down, but not both. And the transverse axis is going to have length 2A. Notice that A squared is always underneath the positive part. So the transverse axis has length 2A, where again the A is under the positive part. The conjugate axis has length 2B, and obviously B is underneath the negative part. The conjugate axis is just an axis. It does not touch any points on the hyperbola. So conjugate doesn't touch any points. Transverse goes from vertex to vertex. There are going to be two foci, which are C units from the center, and they're going to be just on or beyond the transverse axis. They're going to be moving in the transverse direction. However, this C is different from the C with the ellipse. This C is calculated by taking C squared and setting it equal to A squared plus B squared. So instead of doing an A squared minus B squared like we did with an ellipse, C squared is going to be A squared plus B squared. I just want to point out that's going to make C be bigger than A. And so if we do the eccentricity the same way that we did before of C over A, which is exactly what we do, this number is going to be bigger than 1. So the eccentricity for a hyperbola is going to be bigger than 1. Now the last thing is that the hyperbola is going to have two asymptotes. Depending on whether the A is underneath the X part and the B is underneath the Y part, or vice versa, the two asymptotes for a hyperbola are going to have slopes either positive and negative B over A, or they're going to have slopes which are positive, negative A over B. And remember, slope is change in Y over change in X. In this first equation, since the B part is under the Y, the asymptotes will be slope B over A and negative B over A. In this second equation, since the A is underneath the Y, the asymptotes will have slopes A over B or negative A over B. Again, slope is change in y over change in x. So I think about denominator underneath the y versus denominator underneath the x. Let's do a graph of a hyperbola so we can label this information, but then also we'll talk about what a hyperbola is geometrically as well. So what I've done is I've graphed a hyperbola. And my hyperbola is y squared over 25 minus x squared over 16 is equal to 1. So it's a hyperbola centered at the origin. Now, if you calculate the c for, well, first off, I want to point out that since the y part is the positive part, we're pointing up and down. This hyperbola points up and down. We have vertices of 0, 5 and 0, -5. If I go from 0, -5 to 0, 5, that is the transverse axis. And you can see that if this was an infinite axis, then the foci would be on the transverse axis. If I say it's a finite axis that goes from 0, -5 to 0, 5, then it's just beyond. But it's in the same direction as the vertices. That's the point. The conjugate axis would go from -4, 0 to 4, 0. So conjugate moves this way. Transverse moves from vertex to vertex. The foci are 2 points that are sort of beyond or on the transverse axis. In this case, it's 0 and then about 6.4, 0 and then about -6.4. Now, I say that this has asymptotes. You might not see the asymptotes if you're zoomed in this close, because when I'm close to each of the vertices, the hyperbola, when it's close to the vertices, looks kind of like a parabola, or kind of like kind of like a parabola when I'm close to the vertices. However, when you start scrolling out and get further and further away from the vertices, these parabolas edges look more and more like they form straight lines. They get closer and closer to straight lines when we get further away from the vertex. And in this case, let me just graph the lines. Well, in this case, the number underneath the y squared is 25, so square root of 25 is 5. Underneath the x squared, we get 16. Square root of 16 is 4. Slope is change in y over change in x. So if I write y equals 5/4 times x, I'm going to get one of the asymptotes. On the other side, if I take y equals -5/4 times x, I'm going to get the other asymptote. Again, when I zoom in around the vertex, the hyperbola doesn't look super close to these asymptotes. But when you scroll out, as you get your x values bigger and bigger and bigger, the asymptote is really, really, really close to the hyperbola. So those are the asymptotes we're talking about. Now here's the interesting part geometrically. for a hyperbola. If I take a point on the hyperbola, it might be hard to see, but this is the red point here. If I measure the distance from that point to my first focus, and then measure the distance from the point to my second focus, if I subtract these two distances, I will get a 10. In my case, this particular point that I have right now has the first distance being 13.68 and the second distance being a 3.68. So subtract them, you get 10. It turns out every other point has that exact same property. If I measure the distance from one focus to the point, and then measure the distance from the other focus to the point, I'll get different numbers, but when I subtract those two differences, so in this case it was about 11.84 and 1.84, subtract them, I get 10. Every point on the lower half of the hyperbola has that when I subtract d1 minus d2, I get 10. Now on the upper half of the hyperbola, I kind of also get 10, but I have to subtract the other way because this distance is longer. So on the upper half of the hyperbola, if I take the distance from my first focus to the point and the distance from my second focus to the point and subtract, I get a negative 10. So the top half, when I subtract, I get negative 10. But again, we just need to use absolute values and we'd get 10 for every point. So that's the really interesting part about a hyperbola, is that when you subtract the two distances between the foci to the point, then you get a constant number. And that's how we can create a hyperbola through geometry. A hyperbola is the set of all points where the distance from the point to the first focus subtracted from the distance from the point to the second focus is a constant in absolute value. So some of them are going to be 10, some of them are going to be negative 10 in my example. Obviously, it's not always 10. With different hyperbolas, you get different numbers, but with mine, it was 10. So when you subtract those two distances, you get a constant in absolute value. What are we going to do? Well, we're going to find the features of hyperbolas. We're going to find the centers, the foci, the vertices, the eccentricity, maybe some slopes of asymptotes as well. Maybe the length of the transverse axis, the length of the conjugate axis, all of those types of things if we're given the equation of a hyperbola. And then obviously we'll do the reverse. We'll give some features and find the equation. Let's take a look at example 11. Example 11 says find these features of the hyperbola given this equation. If you want, you can push pause on the video and try it yourself. It's very similar to what we did with the ellipse. Now, by the way, I say the positive term is the one with the y, the negative term is the one with the x. Therefore, when we're graphing this hyperbola is going to be pointing up and down. That means that the transverse axis is going to go from vertex to vertex. It's going to be vertical. The two foci are going to be, again, along the transverse axis. The center, obviously, is right in the middle of that transverse axis. So we get that type of scenario. Let's write down all the features that I can, or at least that were on the slide. We had the center. Well, the center is going to be at the point 5, comma, -3. Be careful always when you do that. X minus 5, 5 is your H. Y plus 3 means -3 is your K. The vertices, since we're moving up and down, and since we have 225 underneath our Y part, I take the square root of 225. That's an A of 15. Maybe I should have wrote that down. I will write that down right now. A equals 15. So vertices aren't A equals 15. But the point is that the vertices you're going to get are going to be starting at the center, and then I have to move up 15 units, and then I have to move down 15 units. When I move up 15 units, I get to the point 5, comma, 12. When I move down 15 units, I get to the point 5, comma, -18. Again, that's since A is 15, or excuse me, yeah, 15. Okay. So that's because A is 15, that's where we go with the vertices. And we know we go up and down on the transverse axis. By the way, while I'm here, the transverse axis has length of 2 times 15 or 30. Okay. And if I wanted to talk about the conjugate axis, well, B in this situation is 8. That's the square root of 64. And so the conjugate axis is length 2 times 8, which would be 16. In order to find the foci, let's find the foci next. I would need to compute C. And this is where we have to be very diligent, I guess, is the word. Because calculating the C for the hyperbola is different than calculating the C for the ellipse. We have to use a squared plus b squared to calculate the C. That's 225 plus 64. Now, if I take 225 and add 64, I get 289. Which is really lucky for me because the square root of 289 is 17. Some C values will obviously be irrational. They'll be square root of some ugly number, but in this case, I was pretty fortunate that 289 was a perfect square. That means, since this is true, since C is 17, the foci, I know, we're going to start at the center and move up 17 units, and then start at the center and move down 17 units. So we're moving in the y direction because of how my hyperbola is listed out. When I move up 17 units, I get to the point 514. When I move down 17 units, I get to the point 5, -20. Notice that this is 2 units beyond my vertices. Each focus is past my vertex. Now, if I want to find the eccentricity, well, the eccentricity is going to be C over A once again. In this case, that's 17 over 15, which is a little bit more than 1. Again, well, I'll use an approximate value. An approximate value would be about 1.13, rounded version of that. So that's the eccentricity in this situation. Notice that eccentricity for the hyperbola is always bigger than 1. It could be really big. It could get to some really large numbers. It doesn't have to be just over 1. It could be a very large number, but it's always going to be bigger than 1 for the hyperbola. For the ellipse, obviously it was always between 0 and 1. So these are the key features. Now, if you did want to find the asymptotes in this case, the problem didn't ask for asymptotes, but if you did want to find the asymptotes, since the A of 15 is the part underneath the Y, and the 8, the 64 B squared is underneath the X, so what we would do is we would take the ratio of the piece that's underneath the Y divided by the piece underneath the X, and that would be our slope. So our slope would be 15 over 8. And then obviously we know it goes through this center point of 5, 3. So if I wanted to actually find the asymptotes, I could think of a line going through the origin as y equals slope times x. A line going through any other point is like y minus k is equal to slope times x minus h. So the two asymptotes here would be y minus, again, center there is 5, -3. So y plus 3 equals 15 over 8 times x minus 5. That would be one asymptote, and the other would be just like it, except for slope of -15 over 8. So that's how you get the two asymptotes. The key thing there is the slope is 15 over 8 because the A is 15, that's underneath the y part. The B is 8, that's underneath the x part. And slope is change in y over change in x. And then we know that each asymptote goes through the center. So if you wanted to find the asymptotes, you could. These, the center, the vertices, transverse axis, conjugate axis, foci, eccentricity, those are the more important parts for my class, but asymptotes are interesting as well. Let's go ahead and draw this hyperbola just for the sake of being able to draw it and confirm that we get what we get. All right, so I have drawn, or I've not drawn, I've graphed the hyperbola, obviously in Desmos. You could do this on your calculator as well if you'd like. But we see we have two sides pointing up and down. We see that right in the middle, the center of this is at the point 5,3. If we zoom in, we can see the two vertices, like we said, at 5,12 and 5-18. And if you graph the two foci, they are here at 5,14, 5, -20. So we get that idea. If you wanted to graph and see that the asymptotes were right, I've done that as well. Sure enough, again, at the vertices, the hyperbola looks more like a parabola close to the vertex. But as we zoom out further and further, then the hyperbola goes towards these intersecting lines. So we get these asymptotes there. So that's the idea of a hyperbola. By the way, sometimes when you graph this with a calculator, because of the way the calculator does its graphing, it'll look like it draws the asymptotes. And what it's doing is it's essentially it's plotting points and then connecting the dots. And as it plots the points, let's say, moving up and to the right. And then the next point it plots is the lower left one. So it'll like connect the dots and it'll form and look like it's plotting the asymptote as well. So that's the idea of a hyperbola. So if we have the equation of a hyperbola, then we can find its features. Now, I'm only going to do one example like that, where I start with the equation and then we find the features of the hyperbola. Because it's so similar to problems that we've done before with the ellipse and with the parabola, with the circle, pretty standard type problem. I'm going to, in the next example, do a finding the equation problem. Let's find the equation of a hyperbola with the following properties. It has two vertices. The two vertices of the hyperbola are at point 2, 3 and at point 2, -3. And there is a point on the hyperbola, point on the graph, which is the point 0, 5. Let's find the equation of a hyperbola with these properties. This is the first example we've used a point on the graph to help find the equation of that graph. We'll see how that is done in this example. Before I start using the point on the graph, though, it's important to say we're looking at vertices which are 2, 3 and 2, -3. So the vertices are vertically aligned, and that means that the hyperbola is going to point up and down. In between those two vertices is going to be the center. And so I just need to find the middle there. Did that drawing pretty bad, but the idea there is that we have a hyperbola, and because of the location of the two vertices, I know the hyperbola is pointing up and down. Again, there's my center. So center is halfway between the vertices. That's just the midpoint. And that's pretty easy to find. The midpoint of 2, 3 and 2, -3 is 2, 0. Okay. Also, because it's pointing up and down, I know the type of equation that we're going to be getting. We're going to be getting the type of equation where y is the positive part and x gives you the negative part. Again, we always write the a squared underneath the positive part and the b squared underneath the negative part. Now, the vertices, it's pretty obvious, are 3 units away from the center in the y direction. So that means the distance from the center to the vertices, I'll just write from center to a vertex, is 3, and that's the a. A here is 3. So now I know what my equation is going to look like, except for the b part. I know that the center is at 2, 0. So h is 2, k is 0. That's just going to be y squared when I take y minus 0 and square it. And I know that the a is 3. So a squared is going to be 9. I'm almost to where I want to be. I want to know the equation exactly. I only have one more part of the equation to figure out. The way I figure that out is by using the point on the graph. When you plug in a point on the graph into an equation, it should give you a true statement. So we get a true statement when we plug in the point 0.05. That's what it means to be on the graph. It means that when you plug it in, you get a true statement. If I plug in 0.5, that is 0 into my x value, 5 into the y value, then this equation only has one variable, and I can solve for that. So I can solve for b by solving this, or I can solve this equation for b. Or at least b squared, if I wanted to do that. I think what I'll do here is I will subtract 25 over 9 from both sides. Be careful when you do that. 1 minus 25 over 9 is going to give you a 16, to be a negative 16 over 9. So when you subtract 25 over 9 from both sides, you get negative 4 over b squared on the left, and then on the right, you get 16 over 9. Oh, excuse me, negative 16 over 9. I messed that up. There. And now I can solve for b. I would probably just cross multiply. When I cross multiply, I get negative 36 is equal to negative 16b squared. And then if I divide both sides by 16, I end up getting 9/4 is equal to b squared. So b is 3/2 or 1.5. By the way, you can also do this in decimals. 9/4 as a decimal is 2.25. Doesn't really matter. Decimal, fraction, however you want to use it. All that said, now solving this for b shows me what value of b I need in my equation. So now I know my equation exactly is going to be this, where b is 1.5, or in other words, b squared is 2.25. And that's the equation I was looking for. All of this just came from the fact that I knew the direction my hyperbola was pointing. I could find the center by finding the midpoint of the vertices. I can find the A by taking the distance from the center to one vertex. And then in this case, I found the B by plugging in one point that I knew was on the graph. Obviously, if you want to graph this on your own, you can do that. I'm not going to graph this one. I'll leave that up to you if you want. Here's another example that's more akin to what we did with the ellipse when we were finding the equation of the ellipse. Here I want to find the equation of the hyperbola whose center is at the origin, whose vertex is at 0, 2, and whose focus is at 0, 4. Try this one on your own. If you do that, just push pause on the video. In a couple of seconds, I will show you how it's done. I always find it nice when the center is at 0, 0. I feel good about that. So the center is at 0, 0. Focus is at 0, 2. Excuse me, no, vertex is at 0, 2. Focus is at 0, 4. Again, those are vertically aligned, and therefore I know what's going to happen with the hyperbola directional point. The direction of the hyperbola is going to be pointing up and down roughly. And so if I know that, then I know I'm going to get this equation, the one where the y squared is the positive part and the x squared is the negative part. Now, the distance from the center to a vertex is the A. That's really easy to calculate when our center is at the origin. A is just 2 in this case. distance from the center to a focus is the C, which in this case, again, really easy to calculate, that's 4. We have a hyperbola, so the equation I use for the C is a squared plus b squared is the C. Again, that's different from the ellipse. Be careful about that. In my case, that means 4 squared, which is 16, is equal to 2 squared, which is 4, plus b squared. So b squared has to be 12. And I don't even care about finding b. Obviously, b would be the square root of 12. But in my equation, I need to plug in b squared and not b. So I might as well just leave it as b squared. Center is at the origin. So therefore, the equation that I have is y minus 0 divided by a squared, which was 4. 2 squared is 4. And then x minus 0 squared over b squared, which was 12, is equal to 1. By the way, just as a note, if you calculate the eccentricity on this one, C over A, and this one, it's 2, right? 4 divided by 2 is 2. I'll write that down. So eccentricity doesn't always have to be just a little bit over 1. It can be actually pretty large values in certain circumstances. So this shows you how to find the equation given the center, a vertex, a focus. Obviously, in the last example, we used some other information to find the equation. There's lots and lots of information you can use. I left the y in parentheses. You don't have to if you don't want to. You can get rid of the parentheses if you'd like when we're centered at the origin. But again, straightforward hyperbola in this case, pointing up and down. So far, we've been examining these conic sections, and we've put a lot of emphasis on what the conic sections are, how their graphs are for standard form graphs, how the equations are in standard form, and then we looked at some geometric pieces as well. But most of the problems have been just identify key components and create equations. The last type of question that I said we were going to look at is the identify types of conic sections from their equations. So that's the piece we're going to look at now. If I have nice equations in standard form, then the circle's standard form equation looks like this. The ellipse's standard form equation, or at least one version, looks like this. One version of the hyperbola looks like this. And one version of the parabola looks like this. I want you to notice that if we don't have nice standard form equations, then there are relationships that I can pull out of these standard forms, specifically the squared terms. If I look at the squared terms of a circle, if I expand this out, I'm going to get an x squared. And if I expand this out, I'll get a y squared plus other terms. Now, we all know that if I multiply both sides by a number, then I'll get an equivalent equation. That means if ever I have a number times x squared plus that same number times y squared on the same side of the equation and no other squared terms around, I know I'm dealing with a circle. The same thing is true for the ellipse, although in a different squared terms. If I multiply this out, I get a squared term over a squared. Here I get a y squared over a b squared if I multiply it out. An equivalent ellipse, I'd multiply both sides of the equation by the same number. So that means if the x squared and the y squared terms are on one side of the equation and their coefficients are both positive, then I'm dealing with, and not the same, not identical, because that would be a circle. If they're both positive but not identical, then I get an ellipse. Also, I could have multiplied on both sides by a negative. So if they were both negative on the same side of the equation, but not identical, I'd be, well, I will have been given the equation for an ellipse. That's different with the hyperbola. Notice that the x squared term and the y squared term, one is going to be positive, one is going to be negative when I expand this out. For the parabola, I'll have a y squared term, but I won't have an x squared term with this version of the parabola. With the other version of the parabola, I'd have an x squared term, but no y squared term. So if we're given any polynomial of degree 2 in two variables, x and y, then I can identify the conic section we have by simply looking at the coefficients of the x squared terms and the y squared terms if they're on the same side of the equation. If x squared terms and y squared terms are on the same side of the equation and the coefficients for those terms are identical, then we have a circle. If the coefficients are both positive or both negative when the x squared and y squared terms are on the same side of the equation, then we have an ellipse. If one of the coefficients is positive and one of the coefficients is negative, then we have a hyperbola. Again, this is when they're on the same side of the equation. And if one of the coefficients of the x squared term or the y squared term is 0, meaning I don't see an x squared term or I don't see a y squared term, but I see the other one, then I get a parabola. This gives us a way to really quickly identify conic sections. Let's take a look at some examples. Here are 4 equations that represent conic sections. Remember, all conic sections can be written this way. Ax squared plus bxy plus cy squared plus dx plus ef plus f equals 0 if we're talking about a conic section that I draw in the xy plane. So what we're saying is, as long as we don't have this interaction term, if I have an x squared term and a y squared term, I can just focus on the coefficients there. So let's focus on the coefficients here. I have a coefficient of 1 in front of the x squared term, a coefficient of 4 in front of the y squared term. They're on the same side of the equation. This means that this thing is going to be an ellipse. The second equation, well, the x squared and y squared terms are on the same side. One is a positive, one is a negative. One coefficient is positive, one coefficient is negative. Since they're on the same side of the equation, that means this equation is giving me a hyperbola. One positive, one negative. In this third equation, we see a y squared term, but there's no x squared term around. Therefore, I know this third equation is the equation of a parabola. Now, this fourth equation is a little bit tricky. The current coefficient of x squared is 3. The current coefficient of y squared is 2, but they are on opposite sides of the equation. In order for this rule to work, remember we want it to be on the same side of the equation. If I force these to be on the same side, I would subtract 2y squared from both sides. And I'd get 3x squared minus 2y squared on the same side. One coefficient's positive, one coefficient's negative. Therefore, this fourth equation is the equation of a hyperbola. Let's take a look at a few more examples. On this slide, the first equation has an x squared term, no y squared term. That's a parabola. Oh, by the way, if you want to try these on your own, obviously you can push pause on the video. In the second equation, x squared and y squared are on the same side. Both have coefficients of 4, and therefore we're dealing with a circle there. Identical coefficients dealing with a circle. In the third equation on this slide, notice that we have more than just x squared, but we have x minus 1 quantity squared. That's going to be an x squared, though. If I multiply it out, the first term will be an x squared. This is like having 3x squared on the left-hand side and 2y squared on the right-hand side. If I put these two on the two terms on the same side, I'll have a 3x squared and then minus 2y squared. This equation, therefore, that third equation on this slide, is a hyperbola. In a similar fashion, we have 9x plus 3 squared, 9 times the quantity x plus 3 squared, on one side. And on the other side, I have a minus 4 times the quantity y plus 1 squared. If I put the x squared term and the y squared term on the same side, the x squared term would have coefficient of 9, and the y squared term would have coefficient of positive 4 if I put it on the same side. So that is an ellipse. One is a positive 9, the other is a positive 4 when I put the x squared and the y squared terms on the same side. This shows that we can quickly identify what conic section we're using by just looking at the coefficients of the x squared and y squared terms if they're located on the same side of the equation. We can take one of these examples. This was one of the examples um, and identify this conic section and then convert it to a conic section in standard form. In this case, we'd have to use completing the square to do so. I'll quickly show you how to do that. I don't expect you to do this very often, but I will quickly show you how to do that with this example. In this example, first off, we should note that the identifying the conic, I know this is going to be an ellipse because the x squared and y squared terms on the same side have coefficient of 1 and 4. I think this was one of the ones we did. Now, what I would do is I would probably complete the square on the x component first, and then rewrite it, and then complete the square on the y component second. I'll do that. So if I would do that, I would keep the x terms on the one side, keep x squared minus 6x on the left-hand side, and then all of the other terms are going to get subtracted and put on the right-hand side, at least for now. To complete the square, I know that on the left-hand side, this should be x minus 3. I have a coefficient of 1 here for my x squared. So I just do x minus 3 squared. That's half of negative 6, which means I need to add 9 on the left-hand side. If I do that, I'd also have to add 9 on the right-hand side. So to complete the square for the x, I just do x minus 3 squared is equal to negative 4 times y squared minus 16y, and then minus 20, or excuse me, negative 21 plus 9 becomes a minus 12. So I've completed the square with the x parts. Now I'm going to try to complete the square with the y parts. You could move things around. What I am going to do is I'm going to add 12 to both sides. There's a number of different ways you can do this, but I am going to do it this way. I would get x minus 3 quantity squared is equal to negative 4 times y squared minus 16y. And then I would divide both sides by a negative 4. I'm dividing by that negative 4 because it's a lot easier to complete the square when I have a 1 in front of my y squared part. So I'm going to be doing this, completing the square on the right-hand side of the equation this time. The question then becomes, what perfect square do I need? And I do it the same way I always do. I divide this coefficient of y by 2. 4 divided by 2 is 2. And then I square that, and I say that means I needed to add 4 to both sides of this equation. So I add 4 on the left-hand side, and then add 4 on the right-hand side. Negative 3 plus 4 gives me a 1. And that's what I get. Now it's almost in standard form. All I have to do is essentially add this x minus 3 squared over a positive 4 to both sides. If I add that to both sides, I get 1 is equal to x minus 3 squared over a positive 4 plus y plus 2 squared. If this were any other number aside from 1, I would divide it so I can get the 1 on by itself. Whoops. Normally, we like to see the 1 on the right-hand side. That's usually the standard version. And so this is my equation of the ellipse that I was looking for. X minus 3 squared over 4 plus quantity y plus 2 squared over 1 is equal to 1. So that's just a double completing the square. Obviously, that took quite a bit of time, but it's very doable. There's no hard process in here. It's just complete the square on the x, complete the square on the y. When you do that, you get the x terms on one side to complete the square with the x. When you complete the square with the y, you get the y terms on the one side, and then do the completing the square process. Again, if this were any other number aside from 1, I would divide and get a 1 on the right-hand side. By the way, now that we have this, if we wanted to, we could find all of the features of this ellipse, where the center was, where the vertices were, the length of the major axis, where the co-vertices were, the length of the minor axis, the foci, the eccentricity, so on and so forth. Let's take a look at another example. Let's identify this conic and then convert it into standard form. In this case, I'm already given the x minus 1 squared part and the y plus 1 squared part. So I actually don't have to complete the square in this case. Again, I already have a perfect square with my x, perfect square with my y. By the way, this was one of the problems we had earlier. So when we're identifying the conic, obviously we got 3x squared on the left and then a 2y squared on the right. When I put them on the same side, it'll be a 3x squared and a minus 2y squared. One positive, one negative. That means we have a hyperbola here. If I want to convert this equation into the standard form of the hyperbola, I just need to do some basic algebra in this case. So let's do that basic algebra, okay? What you would do is you would start with this equation. Since I know what a hyperbola looks like, I want to get the two squared pieces on the same side. That's pretty easy to do by subtracting 2 times the quantity y plus 1 squared. And then with a hyperbola, I have something squared over a squared plus minus something squared over b squared is equal to 1. So I need to divide everything by 6. If I divide everything by 6, whoops, on the right-hand side, I'll get a 1. When I divide by 6, that first term by 6, 3 divided by 6 is like 1/2. So I will be getting x minus 1 quantity squared divided by 2. That second term, when I divide by 6, is going to be a 2 divided by 6. So 2 over 6 is just a 3. And that is the standard equation for the hyperbola we were looking for. Notice that it was a lot easier than our last example because we had already been given the completed squared terms. So we didn't have to do the process of completing the square. Now that I have this hyperbola, if I wanted to, I could find all of the features. I could find the center, the two vertices, the two foci. I could find the asymptotes. I could find the eccentricity. I could find length of the transverse axis, length of the conjugate axis, all of those features that we try to find with a hyperbola. I'm not going to do that in this example because it didn't ask me to do that in this example, but you could. Now, the last thing I want to talk about is the concept of this eccentricity. We've already seen that the ellipse has eccentricity always between 0 and 1. And the hyperbola always has eccentricity greater than 1. It turns out that the circle and the parabola also have eccentricities, but they're always the same. Every circle has eccentricity of 0. Every parabola has eccentricity of 1. So ellipses and hyperbolas have eccentricities that can kind of range. I've already talked about the eccentricity of the ellipse. I said that as the ellipse gets closer and closer to a circle, the eccentricity gets closer and closer to 0. As it gets more stretched out, that eccentricity gets closer and closer to 1. I'll talk about the hyperbola in a moment, but notice that when you get closer and closer to 1, in some instance, you can think of that as closer and closer to a parabola. So the more stretched, a really, really stretched out ellipse may start looking like a parabola. I'll show you the connection to the cone and why the eccentricity is that way right now. So we started out with this sort of a picture where we had our intersection of a plane and the cone formed out the equation or formed out the conic section object. And I think it's easier to rotate the plane. This is going to be a little bit confusing because we're thinking of this plane as being like the XY axis, although it's not graphed as the XY axis in this three-dimensional figure. But when I look at this, if the plane that I'm cutting through, the cone, has slope 0 in the XZ direction, then the object that I cut is going to be a circle. Now, obviously, if I move this plane up along the cone, I still get a circle just with larger radius. So every circle can be formed by cutting a plane through the cone at slope 0. The side of this cone in a standard three-dimensional cone rotated around has slope of 1 if you think about it in the xz direction. As the slope of this plane starts growing anywhere from between 0 and 1, then the plane is cutting this cone, and the intersection of the plane and the cone is forming an ellipse. So as A grows, we get basically, it starts out as a circle, and then as the slope grows, it stretches out that ellipse out more and more and more. The closer to 1, the more stretched out that ellipse is. Now this is really close to 1. Here, what if we actually hit 1? Well, once we've hit 1, now we have exactly the parabola. And once we're beyond 1, then we have some version of a hyperbola. Now notice as the A starts growing, what's happening with this hyperbola. This is a sharper and sharper corner as the A grows. As the A grows, we get sharper and sharper corners. As we get closer and closer to 1, that corner is less sharp. So for like something like 1.25, where this corner turns, I say corner, it's not an actual corner, but where the hyperbola turns at the vertex, it looks more parabolic shaped. And if the slope grows, it looks a little bit more like the absolute value graph, a little bit sharper on that turn. Okay. Now, I say all that to say all of these things are showing that the eccentricity is related to how this plane cuts the cone. If it's 0, slope of that plane is 0 in the xz direction, then we got a circle. Anywhere between 0 and 1, we have an ellipse. That ellipse stretches out more and more and more and more and more until we hit the value of 1. At the value of 1, we got a parabola. And then at a value greater than 1, we cut it through both sides of the circle, or both sides of the cone, and we get a hyperbola. So eccentricity is essentially telling me how my plane cuts through that cone from 0, then up to 1, and then beyond 1 there. 0 gives you the circle. 0 to 1 is an ellipse. At 1, we get a parabola. Above 1, we get a hyperbola. And by the way, this is the only time it only cuts through, like the parabola here can be thought of essentially as an ellipse, which we've stretched out to infinity in some sense. That's why the corner of the ellipse, where the vertex is, looks very similar to the corner of a parabola. I say corner. Where the vertex of the parabola is and a vertex of an ellipse look very similar shapes. So that's what the eccentricity tells us. When we're talking about the eccentricity of an ellipse, closer to 0 is closer to that perfect circle. Closer to 1 is closer to a parabola, so a stretched out version of the ellipse. The hyperbola, when it's closer to 1, it looks like two parabola type shapes. And when it's closer to infinity, at the vertex, it looks sharper and sharper and sharper, almost like a V instead of a U shape on the parabola. Okay. So that's what eccentricity tells us. That's why it is the way it is. You can actually visualize this in 2 dimensions as well by messing around with the formulas for both the ellipse and the hyperbola. So we'll do that in 2 dimensions as well. So here I've graphed a hyperbola whose center is at the origin, and this has just numerical values where I can change the A and the B, but it's always going to be a hyperbola pointing up and down. If I want to calculate the eccentricity for the one I've graphed right now with A of 1 and B of 2 is a 2.24 roughly. As I start increasing the value of the B, notice what happens. As the eccentricity gets more and more and more, this is a more rounded curve. And so close to the origin, it's going to look a little more like 2 flat lines. So as you start increasing that eccentricity, because this is more, well, it starts looking flatter and flatter. The hyperbola starts looking flatter and flatter. And as you zoom out, it looks like 2 straight lines. Excuse me. So in 2 dimensions, that's what it starts looking like. Looks like flatter and flatter. And as the eccentricity gets closer and closer to 1, these things get sharper. These things are coming in contact. I might have said the reverse in the other one. But the point is we're getting things that point up and down very steeply. So the eccentricity, in one sense, is telling me something about the steepness of the asymptotes. Okay. And it always kind of depends on how you draw it. But as you get bigger and bigger and bigger eccentricities on the hyperbola, these look like 2 flatter lines. The slope of the asymptotes are small. In this case, when they're pointed up and down. If our eccentricity gets closer to 1, then the asymptotes are really steep in this case. Okay, so that's the idea there. You can also do this with the ellipse by playing around with it. Obviously, if A and B are the exact same numbers, we have a circle. So the eccentricity of the ellipse would be 0. But as I start increasing, let's start making A the bigger number. Increasing more and more and more and more and more. Eccentricity starts getting closer and closer and closer to 1. It's a more stretched out ellipse. Again, this is an ellipse with eccentricity of 0.996. So that's the idea of eccentricity. We can see that visually, both with the cone and in the two-dimensional space. By the way, again, just thinking of this hyperbola as we get steeper and steeper, eccentricity is getting higher and higher. If you zoom in more and more and more, again, it's starting to look this way. It's kind of a hard thing to see on the hyperbola. The hyperbola is weird to visualize because you can zoom in and out. And if you zoom out really far, it's almost always going to look like like very sharp turn. And if you zoom in close enough, it always looks like a smooth U shape. So hyperbola is a little bit weird, but that's all right. That's the way it is. All right. It's the way it goes. So there we go. That's the idea of eccentricity. All the other ones are pretty straightforward. Circle, 0. Ellipse, anywhere between 0 and 1. And then the parabola at 1. So this concludes a very long video on conic sections. We dealt with these, the circles, the ellipses, the parabolas, and the hyperbolas. Obviously, we avoided the trivial conic sections of a point and a line and 2 intersecting lines. But we saw a lot of features of circles, ellipses, parabolas, and hyperbolas. We saw how they come from the actual cone intersecting the plane, and we saw they're two-dimensional in the XY plane equations and did all of that kind of stuff. Again, this was a very long section, a long video on conic sections. In this case, probably one of the longest videos in the Calc 2 course that this is included in.